A 25 kilogram box is at rest on the floor. The coefficients of friction are mu static equals 0.28 and mu kinetic equals 0.20. If Mr. Tang applies a force of 300 newtons, 30 degrees below the horizontal, will the box move? All right. So in this problem, we have a box at rest. I try to push it. Is it going to move? Is it going to move? That is to say, is it going to overcome the static friction? I'm going to start with a free body diagram of the box. This free body diagram should contain the force of gravity, at this point, you may be tempted to draw the normal force upwards, the same size as the force of gravity. However, this would be wrong. The normal force is not going to be the same size as the force of gravity. If you remember from the previous video, when we push at an angle below the horizontal, we're actually adding an additional force going downwards, which means the normal force is going to have to be bigger. It's got to balance both of them out. So it's actually better to draw the applied force first. So I'll draw the applied force here at approximately a 30-degree angle. I labeled that pretty strategically, actually, because what I'm going to do is break it into components. Horizontal and vertical, with a 30-degree angle being right here. That's what it means when it says 30 degrees below the horizontal. So the hypotenuse is the actual applied force. That's why I labeled it where I did. Whereas the two legs we call these the two components. I will label with FAX for the horizontal and FAY for the vertical. Only after drawing that am I able to draw the normal force. The normal force has got to be the size of the gravity and the downward component of applied force together. I'm going to write out the statement for that. So I said the normal force, that's the upward force. In magnitude, it has to equal the two downward forces in magnitude. So that's gravity plus y component of applied force. Okay, the upwards normal force must balance out the downwards gravity and downwards y component of applied force. And that leaves us with friction. Now, friction I actually don't know how long to draw, because the question is, will the box move? Okay, will the box move? So if the applied force in the x direction, so if the x component of the applied force, if that's bigger than friction, then it will move. If not, then it won't. All right, and I really don't know if it is or not yet. So I just drew it kind of ambiguous there. Hard to tell in my diagram if it's bigger or not. Okay, now let's go on to try to solve this. Now, I can take the approach where I do everything in variables. So I plug in equation after equation until I get a final equation in there. However, I think for the sake of easier understanding, I might actually use numbers pretty early here. Okay, so I just labeled the mass there as 25 kilograms. And my applied force, this hypotenuse here, it's actually 300 newtons. We're given that as well. So I'll throw that in here as well. Okay, and keep in mind we know our coefficients of friction. Okay, they're right here. Well, I'm really only worried about the static one. Okay, the static coefficient is what I'll use to figure out if this thing's going to move or not. All right, I'm going to start by calculating a few forces out in this free body diagram. Starting with gravity. Gravity I know is mg, so I can calculate that rather quickly. So the mass is 25, and multiplying that by 9.8. So I get 245 newtons for gravity. Okay, what else can I calculate out? Well, I can actually calculate the components of the applied force. I have that drawn in red here. Because I know the hypotenuse of that triangle, and because I know one of the angles, 30 degrees, I can use SOHCAHTOA to figure out my components there. So I'm going to do that, find a little space to do that. So I'll start with the x component. Now that's the adjacent side to 30 degrees. So with SOHCAHTOA, I'd be looking at ka. So cosine of 30 degrees will equal my adjacent side divided by my hypotenuse. And my hypotenuse is 300 newtons. So multiplying both sides by 300 newtons, I can figure out my x component. All right, so I'm getting a 260. So 260 newtons for the x component of gravity. I'll do the y component. Now the y component is the opposite side of 30 degrees, so it's going to be SO, or sine, of 30 degrees equals opposite over hypotenuse. Hypotenuse is 300. And multiply both sides by 300. That gives me 150 newtons. So I have the two components of the applied force there. And you know what? That allows me to get the normal force. Okay, looking back all the way to the top here, okay, my normal force has to equal the force of gravity plus the y component of applied. So I have those two numbers now, 245 plus 150, giving me a normal force of 395 newtons. And now that I know my normal force, I can find the force of static friction, the maximum static friction, that is. Remember, static friction is a range of values, or it can take on a range of values. I'm going to calculate the max value that it is by doing mu static times the normal force. So the static coefficient is 0.28. The normal force I just calculated is 395. So I'll multiply that out. And I get 111 newtons. I get 111 newtons. So my friction is 111 newtons. That's the maximum static friction. So the question is my applied force big enough? Okay, so I'm going to highlight what matters now. What matters is this number, 260. That's the x component of the applied force. That's the amount of force going towards the right. 260 newtons to the right versus 111 newtons to the left. So yes, it is big enough to move it. Okay, so I will say, oops. The x component of the applied force is larger than the maximum static friction. So it will move. So it will move. Okay, good. That answers the question. I'm actually going to extend it a little bit. I'm also going to, I'll add a part B here. Now that I know it moves, I'm going to try to find its acceleration. Assuming that, I'm going to stick with the 300 newtons applied force, it's going to cause it to accelerate. What's the acceleration going to be? Well, the acceleration is going to be the net force divided by the mass. That's Newton's second law. So we don't forget about the older formulas. Now the net force, be careful. You may be tempted to write 260 minus 111 for the net force. And the mass is 25. However, that's wrong. Okay, that's not correct. Because 111, that was for static friction. But now that it's moving, we got to switch to kinetic friction. So I'm going to erase the 111. So I have to do a little bit more work to find the kinetic friction. Okay. So the kinetic friction is simply mu kinetic times the normal force. So all that's different is the coefficient. So it's the kinetic coefficient is 0.20. My normal force is the same, 395. So I get a new value for friction here, 79 newtons. Okay, so that's what I can fill in for the net force. So 260 to the right, okay, minus the 79 newtons of friction, that's the net force. Calculate that and divide it by the mass of 25, and that'll give us the acceleration. And that gives me 7.2 meters per second squared. That's quite a large acceleration. I probably will not push it that hard for that long. I'll probably just get it moving and then drop the force down in real life. to get it going at constant velocity. All right, so that's this one. So next in the hand-in folder, there's a similar one for you to do. The one in the hand-in folder is different though. Instead of pushing at an angle below the horizontal, it's pulling at an angle above the horizontal. Okay, so you're going to have to make some adjustments. Basically, that's going to adjust the normal force. And you may have to go back to the previous video if you forgot what the difference is going to be between the two cases. But your normal force will be calculated in a different way for that question. I also picked out a couple of questions from the textbook I'd like you to try as well. So then that'll be, I think, 3 questions in total for you to do. Submit it to the folder. I can give you some feedback. And then that'll be it. That'll be the last thing for this unit other than the problem set. Okay, you'll have another problem set to do this week. Okay, so I look forward to seeing your work, and congratulations on finishing this unit.